So usually when we sit down for these deep dives, we just sort of wander around a topic. We look for the cool stuff.
Yeah, we like the shiny objects.
Exactly. But today is a little different. Today feels less like exploration and more like survival.
Survival is a strong word, but honestly,
Hmm.
looking at the job market right now, especially for tech, it feels appropriate.
It really does. I was scrolling through job boards this morning, just out of curiosity, I promise.
Sure, sure.
And the requirements for AI roles, they have shifted dramatically. 2 years ago, if you could spell GPT, you were hired.
Those were the days.
Now, it looks like you need a PhD in applied math just to get an interview.
It tracks, though. We have that artificial analysis state of AI report in the stack today, and it shows just how fast the field is moving.
It's moving fast.
We went from those simple chat apps in 2023 to reasoning models, and now heading into 2025, everyone is talking about embedded agents.
Right. Systems that don't just talk, but actually do things.
Exactly. And because the stakes are higher, the bar for entry has just skyrocketed. Employers are done with the fake it till you make it crowd.
They want to know if you actually understand how the engine works.
That's it. Anyone can drive the car. They want to know if you can fix the transmission. Can you explain the math behind the curtain?
So that is our mission today. We have curated what I am calling the ultimate cheat sheet.
A cheat sheet is good.
We found the 12 most critical technical interview questions, the kind that separate the casual enthusiasts from the actual engineers.
And we are going to walk through them one by one.
Consider this your 12-step program to acing the technical interview. So grab a notebook or just open a notes app because we were going straight into the deep end.
Let's do it.
Section 1, the foundations. Question number 1. It sounds simple, but I feel like it is a trap. What is machine learning?
It is absolutely a trap. If you give the pop culture answer, it's when computers think like humans, you've probably lost the job right there.
Okay, so what is the engineer's answer?
You need to be precise. Based on the Introduction to Symbolic AI paper we read, you should define machine learning as the study of algorithms and statistical models.
Okay.
But the key is that they improve performance on a task automatically through patterns and inference.
Patterns and inference. That is the magic phrase.
It is. You have to contrast it with what came before. Traditional coding, what we call symbolic AI, is rule-based. It's logic.
Like if X happens, do Y.
Exactly. It's a recipe book written by a human. But machine learning is sub-symbolic. You don't give it the recipe. You give it the ingredients and a picture of the final cake, and you say, figure out how to bake this using statistics.
I really liked the onion analogy from the BMC blogs source we looked at.
Yeah, that's a great visual for an interview. Imagine AI as the big outer peel. That encompasses everything, even the old-school rule-based systems.
Right.
Inside that, you have the machine learning layer. That's the statistical tools we just defined. And then right in the intent center, you have deep learning.
Which we will get to in a bit. But sticking to that middle layer, machine learning, brings us to question number 2. If I'm building one of these systems, what do I actually need? What are the 3 core pillars of a machine learning system?
If you are whiteboarding this, you draw 3 boxes: data, model, and learning.
That sounds a bit generic, though. Data seems obvious.
It's not just stuff, though. This is a crucial distinction from the Mathematics for Machine Learning textbook. To a machine, data isn't text or pictures.
What is it then?
It has to be converted into vectors.
It does, so lists of numbers.
Exactly. The computer can't read a resume. It reads a vector representation of that resume. So pillar 1 is data, specifically numerical representation. Pillar 2 is the model.
And the model is just the code.
Think of the model as a hypothesis. It is a mathematical structure, like a formula with a bunch of empty slots, that is waiting to be tuned. It is a block of clay waiting to be shaped.
Okay, so we have the clay. What is the 3rd pillar?
Learning. This is the optimization process. It is the bridge that connects the data to the model. It is the actual act of sculpting that clay to match the reality of the data.
So data is the material, model is the shape we want, and learning is the sculpting tool.
That is a solid analogy. I like that.
I try. Okay, moving to question number 3. We know what the system is, but how does it actually learn? This is the classic showdown. Explain the difference between supervised and unsupervised learning.
This is usually where people get sloppy. The high-level distinction is simple. It is all about the labels.
Labels?
Yes. Supervised learning uses labeled data. The IBM source we have puts it perfectly. The ground truth is provided.
So you give it the answers.
Right. You show the machine a picture of a cat, and you attach a digital sticky note that says, "This is a cat." You are the teacher holding the answer key.
So it's basically just memorizing flashcards.
In a way, it is mapping inputs to known outputs. Classification like spam or not spam is the classic example.
Okay, so unsupervised learning must be the opposite. No teacher.
No teacher, no answer key. You throw the student into the library and say, find the patterns. The model has to find hidden structures in the data on its own.
The Wikipedia source had a really cool example of this, using a geyser, right? Old Faithful.
Oh, I love this one. So researchers had all this data about when the Old Faithful geyser erupted and for how long. But they didn't label it. They just fed the raw numbers into an unsupervised algorithm.
And what happened?
The computer didn't know what a geyser was. But it successfully clustered the data into two distinct modes: short wait, short eruption, and long wait, long eruption.
It discovered the physics just by looking at the clumps of numbers.
Exactly. So supervised is, here's the answer. Unsupervised is, go find the structure.
And here's a pro tip I saw in the notes. If you want the brownie points, mention semi-supervised learning.
Oh, definitely. Labeling data is expensive and slow. Humans have to do it. So real-world systems often use a tiny bit of labeled data and a massive amount of unlabeled data.
Okay, foundations are laid. We know what ML is, we know the pillars, and we know the styles. Now let's move to section 2, the agent and the brain.
This is where things get a bit more sci-fi.
Question number 4 involves a totally different way of learning. What is reinforcement learning, or RL?
RL is a different beast entirely. It is not about classifying cats or clustering geysers. It is about an autonomous agent making decisions.
So it involves action.
Action is key. The source, an introduction to reinforcement learning, breaks it down into a loop. You have an agent. The agent observes this state. It takes an action. And then, this is the most important part, it receives a reward.
Or a punishment.
Right. Think of a mouse in a maze. That is the classic analogy. If the mouse finds the cheese, positive reward. If it hits an electric fence, negative reward. The goal isn't get the right answer. It is maximize cumulative reward over time.
I notice a term in the notes here that sounds like a life philosophy: exploration versus exploitation.
It really is a life philosophy. In RL, this is the central dilemma. Imagine the mouse finds a path that leads to a small piece of cheese. That is reliable.
Okay.
Does the mouse keep taking that path?
Yeah.
That is exploitation, using what you know. Or does it risk trying a new dark tunnel that might lead to a giant block of cheese or might lead off a cliff? That is exploration.
And the math has to balance that.
It does. If you only exploit, you never improve. If you only explore, you never succeed. In an interview, drop the term epsilon greedy. It is a specific algorithm used to mathematically balance that trade-off.
Epsilon greedy. Got it. Okay, question number 5. This is the big buzzword. How does deep learning differ from standard machine learning?
Remember the onion. We are in the center now. Deep learning is a subset of ML that uses multi-layered artificial neural networks.
Is it just more layers, or is it doing something different?
It is doing something fundamentally different regarding features. In standard ML, you usually have to tell the computer what to look for. That is called feature engineering.
Like, look for these specific keywords.
Right. But in deep learning, the network figures it out itself. It builds a hierarchy. The sources explain that the bottom layers might just detect edges or lines. The next layer combines those lines to see shapes. The top layers combine shapes to see faces.
It learns the concepts from the bottom up.
Exactly. But, and this is the gotcha for the interview, this creates the black box problem.
Right, the explainable AI source mentions this.
Because the network built its own features in these hidden layers, we often don't know why it made a decision. It is opaque.
If you are applying for a job in banking or healthcare, you need to acknowledge that.
You can't just use a black box to deny someone a loan without knowing why. You need to show your work.
And hey, if you really want to show you are on the cutting edge, mention Geoffrey Hinton.
The godfather of AI.
The same. He recently published a paper on the forward algorithm. He is actually questioning the way these networks learn, suggesting we might not need the traditional methods we were about to discuss.
Dropping that reference shows you aren't just reading textbooks from 2018. It shows you are following the active research.
Nice touch. Okay, moving on to section 3. I call this section When Things Go Wrong, because let's be honest, the model rarely works the first time.
Never. It never works the first time.
Question number 6 helps us diagnose the most common problem. What is overfitting?
Overfitting is the nightmare scenario. It is when your model memorizes the training data so perfectly that it fails to generalize to new data.
It is the student who memorizes the exact answers to the practice test but fails the actual exam because the phrasing is slightly different.
That is the perfect analogy. Visually, imagine a graph with data dots.
Mm.
A good model draws a smooth curve through the trend. An overfitted model draws a squiggly, chaotic line that hits every single dot.
It is fitting the noise, not the signal.
Exactly.
And this isn't just a technical bug anymore, is it? We have some sources here about copyright law that link back to this.
This is huge right now.
Hmm.
The paper on generative AI training and copyright argues that overfitting is legally dangerous.
How so?
Well, if a generative AI model memorizes the training data too closely, it can reproduce copyrighted works verbatim.
So instead of learning the style of a sci-fi novel, it just accidentally writes Dune word for word.
Exactly. That is not learning, that is a photocopier. And that gets you sued. So knowing how to stop this is critical.
Which leads perfectly to question number 7. Name 3 techniques to prevent overfitting.
The Holy Trinity. Regularization, dropout, and early stopping.
Let's run through them. Regularization.
Think of it as a tax on complexity. You add a penalty term to the math equation, the loss function. If the model tries to get too squiggly or complex, the penalty gets higher. It forces the model to stay simple.
Keep it simple. Okay, what about dropout?
The dropout is wild. During training, you randomly deactivate or turn off massive chunks of the neurons.
You break the brain on purpose?
Temporarily.
Yeah.
It forces the network not to rely on any single neuron or path. It's like training a sports team by randomly benching your star player every other game. The rest of the team has to step up and learn the plays.
That makes sense. And early stopping.
That is exactly what it sounds like. You watch the validation error. The moment the model stops learning the pattern and starts memorizing the noise, you pull the plug. Stop training immediately.
Question number 8 helps us balance this. What is the bias variance trade-off?
This is the seesaw of machine learning. You cannot usually minimize both bias and variance at the same time.
Why not?
Because they are opposites. A simple model, like a straight line, has high bias. It oversimplifies the world. It assumes the world is linear when it might be curved. That is underfitting.
Okay, so simple equals bias.
But a complex model, that squiggly line we talked about, has high variance. It is hypersensitive to tiny fluctuations in the data. That is overfitting.
So if the interviewer asks, can you make bias and variance both 0?
You say no. You have to find the sweet spot in the middle. That is the art of the job.
All right, brace yourselves. We are entering the final stretch. Section 4, the mechanics of learning. This is where we get into the heavy math.
This is where you prove you are an engineer, not just a prompt writer.
Question number 9, why is k-fold cross-validation used?
This connects back to checking your work. You need to know if your model works on data it hasn't seen. That generalization we talked about.
Right.
But if you only have one data set and you just split it once, say 80% for training and 20% for testing, you might just get lucky.
Maybe your test set happened to be the easy questions.
Exactly. So k-fold fixes that. K is a number, usually 5 or 10. You split your data into 5 chunks. You train on 4, test on 1. Then you rotate. You do it 5 times so every chunk gets a turn being the test set.
It is a reality check to make sure you aren't fooling yourself.
It gives you a robust estimate of generalization error. Use that term in the interview, generalization error.
Got it. Question number 10. We mentioned this earlier, but let's define it properly. What is the role of backpropagation?
Backpropagation is the blame game.
The blame game.
Technically, it is the efficient application of the chain rule from calculus.
Oh boy, high school flashbacks.
It is useful. Imagine the network makes a mistake at the output. Say it thinks a cat is a dog. You calculate the error, or the loss. Backpropagation works backward through the layers to figure out which neuron contributed to the error and how much.
It identifies who messed up.
It calculates the gradient of the loss with respect to the weights. It says, you voted dog, you were wrong, lower your influence next time. This feedback loop is the actual moment the machine learns.
Question number 11. How is data typically represented in machine learning? We said vectors earlier.
Yes, but let's go deeper. In a data set, your rows are examples, like specific customers. Your columns are features, age, salary, location, previous purchases. To the computer, this is a matrix.
And there is a warning in the notes here about the curse of dimensionality.
This is critical. You might think, more data is better. Let's add 1,000 columns of features.
Why is that bad?
Because geometry gets weird in high dimensions. As you add more features, as you add more dimensions, the space becomes incredibly sparse. The data points get so far apart that the model can't find patterns anymore.
So just throwing more columns at a problem can actually break it.
Exactly. A smart engineer knows when to reduce dimensions, not just add them.
Final question, number 12, the engine of the whole enterprise. Describe gradient descent.
Gradient descent is the optimization algorithm. It is how we find the minimum error.
Give us the visual. How do we explain this without a whiteboard?
Imagine you are standing on top of a mountain at night in a thick fog.
Okay.
You want to get to the village at the very bottom, the lowest point, which represents zero error. But you can't see the village.
You can't just run down.
Right, you'd fall off a cliff. So you feel the ground with your foot. You feel the slope, the gradient. If it slopes down to the right, you take a small step to the right.
And you just keep doing that.
Step by step, always moving opposite to the incline. That is gradient descent. You are iteratively adjusting the parameters to move down the error surface until you reach the minimum.
And there we have it, the 12 steps. We've gone from the high-level concept of inference versus rules through the onion of deep learning, the mouse in the maze of RL, and all the way down to the mountain in the fog of gradient descent.
If you can articulate these 12 points clearly, using these analogies and precise terms like vectors, backprop, and dimensionality, you aren't just faking it. You actually understand the bedrock of the field.
Before we let you go, though, I want to circle back to something we touched on with overfitting. We have talked a lot about the math, but I can't stop thinking about that legal source we mentioned, the Generative AI Training and Copyright Law paper.
It is a huge topic. We've spent this whole time explaining how machines learn patterns. But there is a real debate happening right now about whether that learning is actually ownership.
Right. We just explained that ML models are effectively giant statistical mirrors. They learn vectors and weights based on data we created. If I read a library of books and write a new novel, that is inspiration. But if a machine processes a library of books into vectors and outputs a similar novel, is that inspiration?
Or is that just a high-tech photocopy?
Exactly.
And as that artificial analysis report showed, we are moving toward agents, AI that does things. When an AI agent takes an action based on data it learned from a human creator, who owns that action? Who owns the output?
That is the question they probably won't ask you in the coding test, but it is the one that might define the industry you are trying to join.
Absolutely. The math is settled. The implications are just getting started.
That is it for this deep dive. Good luck with the interview prep. Go memorize those definitions, but more importantly, try to understand the concepts.
And keep an eye on those scaling laws.
We will see you next time.